my main work is consulting for the implementation of the Stockholm Convention, working for the Stockholm Convention Secretariat or UN agencies or governments. But at the same time, I have a good link to research community, and so today the topic of my talk is a Stockholm Convention implementation, possible tasks for researchers. Today we will look to Stockholm Convention and the global monitoring, the PBDE as new POPs, the challenges and the knowledge gaps, and PFOS as first fluorinated new POPs. And during the presentation I will first try to highlight some research topics for the research community, and also give maybe some case studies which can be repeated in similar way in other countries. That's the ideal. Actually, the Stockholm Convention text start with Rio. Yeah? In the first article, this say mindful of the precautionary approach as set forth in the Principle 15th of the Rio Declaration. We want to protect human health and the environment from persistent organic pollutants. And one challenge I see as a researcher is that the people in UN sometimes have not a direct link to the research community, and also the research community don't have the detailed idea what in conventions happen. And in the presentation before, we saw that only 40 of the chemicals are regulated. Yeah? One reason is that the regulator are not too much aware. Yeah? And we have to think strategies how to make impact that our voice from the science come up to practice. We have very good examples in history where we see, for example, Rachel Carlson with her Silent Spring book. She reached the public and also the policy makers. Or when Meadows brought the limit of growth, just at that time then, mainly because of this book, environmental agencies were funded, yeah, in the beginning of the 70s. For the Stockholm Convention or Global POPs Convention, the start was then in the 1990s, when it was found that POPs are found in the Arctic, yeah, so that not only the own government is responsible for their own area, but that we emit in one country and impact people in other countries and other regions. And then around 1998, a scientific consensus was reached, and the POPs protocol, first the UNECE, was funded for the region of the North and the European Communion. And 3 years later then, the POPs were brought up to the global by making the Stockholm Convention. It needed then 3 years to convince about 50 countries to ratify that. Finally in 2004, then the Stockholm Convention came into action. So another topic where the scientific community gave the input is to define a POPs. We know it's the chemical need to be persistent, bioaccumulative, impact to human health, and have a potential long-range transport. These were defined by the scientific community, but are still discussed. Yeah, if now the definition of the POP, how it is in the convention, is appropriate, or if there will be some changes necessary in future. Meanwhile, 172 countries have ratified the convention. You see here that more or less whole South America, whole Africa. The main countries which are missing is the US and Russia and Greenland. And these are the compounds we have in the Stockholm Convention. First, the 12 POPs, 30 dozen. Most of you will know. There are a range of pesticides, including DDT, endrines. Then we have 2 industrial chemicals. This is hexachlorobenzene and PCBs. And we have so-called unintentionally formed POPs. These are chemicals which come out of processes like incineration or the metal industry, which are not formed intentionally by the industry. And since 1 year, the convention made a large step forward because 9 new POPs were added. Yeah, including this time also brominated compounds, the pentabrominated diphenyl ethers, the octabrominated diphenyl ethers, the hexabromobiphenyl, and we have first time also a fluorinated compound, PFOS, all industrial chemicals. And additionally, some more pesticides were added, the HCH and lindane, pentachlorobenzene, and another pesticide, the chlorodecone. And currently, we have in the process of evaluating chemicals 3 candidates. These are endosulfane, short-chain chlorinated paraffins, and hexabromocyclododecan. And actually, here our colleague from Chile, the last 3 years, I think he could not sleep because of endosulfane. He was responsible for the POP reviewing committee group. And when you are interested in this topic, you can discuss with him. But it came to a good end. We will hear later. We don't know yet. Yeah. Okay. So how does the Stockholm Convention work, and where might the research come in? I have made here a list of the activities in the Stockholm Convention and marked the areas where I think there might be the research in red. So we have elimination of POPs, we have restriction of POPs like the DDT, these are, or PFOS, these are chemicals which are not completely forbidden. Yeah, where for DDT you still have, for the vector control, it is allowed. Yes, so it is not complete elimination, it is restriction, and countries have to ask if they want to use DDT. Management of stockpiles and waste, find POPs contaminated sites, preparation of national implementation plans, which are normally now done mainly by the governments without the discussion with the research community in most countries, listing of new chemicals, which are based, of course, on science, but in my opinion, where still the science can be brought much more in. Then we have an article on promotion of research, which is currently not too much addressed when you read the national implementation plans. Technical assistance and financial mechanism, exchange of information, reporting, and effectiveness evaluation. And actually today, mainly the research community come into play when it comes to effectiveness evaluation. Yeah? What is effectiveness evaluation? We have now the convention, and of course the convention need to have a mechanism which tell if the convention works or if the convention don't work. Yeah, and this want to be done with measurements. So therefore the establishment of arrangements to provide itself with comparable monitoring data on the presence of the chemicals which are listed in the convention, as well as their regional transport, and this is done in the Global Monitoring Project. The objective here of the Global Monitoring Project is to provide a harmonized organizational framework for the collection of comparable monitoring data and or information on the presence of the POPs listed in the convention in order to identify trends in levels over time, as well as to provide information of their regional and global environmental transport. We have 6 regions. You see here South America is together with Middle America in the GRULAC regions. And in the first part now of this global monitoring program, the minimal requirement to reach is that baseline data from all regions for further evaluations are established. To have core data here for air and for human milk. These are the 2 effectiveness evaluation matrices, and establish strategic arrangements and partnerships, and develop regional reports prepared for the conference of parties. Yeah? And here already there have been 1 round of this reporting. What we see is that, and this is I think a very good effect, there is already a strategic partnership in ambient air where all the large monitoring networks now collaborate with each other. This means AMAP, IMAP, Japan is mainly leading this East Asian countries monitoring. Then GAPS, where Frank is in, Rizitox in Brno with Professor Holubek for East Europe and the UNECE. But we have to take care and also one time reflect how useful is to monitoring old POPs which are not produced anymore. Because actually it's clear what we will see is a decreasing time trend. Yeah, and this decreasing time trend will come to the policymakers. So actually, therefore, when I go to like this workshop, I bring a small present that was for you, Joao, the toxic consumer. So this was just the last presentation, yeah. Because actually, normally with the Stockholm Convention, you talk about the old chemicals, and we see, okay, effectiveness, the things are decreasing. So we have to take care that the policymakers become aware that we have problems with chemicals. So then we have the strategic partnership for human milk with the WHO, UNEP and the Stockholm Secretariat. There were WHO rounds for human milk 2001, 2004, 2005, 2007. Actually at that time more or less no developing or transition country participated. It were mainly the industrial countries. So you have for example no African country. In the third round only Egypt, and this was eight women which were paid some money, yeah, and of course, yeah, Brazil participated, okay. And now this time in 2008, we have made a complete round of more or less only developing and transition countries. And here I see a very nice task for the research community, because actually normally these human milk projects are also done by the government, and then you just send one pool sample to the WHO laboratory, analyze it for the POPs. But this can also be combined with research. This we did with Ghana. Ghana did a very nice human milk study, 120 participants in 6 different cohorts, and at the same time 2 PhD theses were made. Yeah, and these two PhD students, they analyzed then also, or they're currently analyzing also then the single compounds of the different participants, that you not only have the data of the pool, and actually they will analyze more brominated flame retardants, also the modern brominated flame retardants. And we did one try with Shimatsu Techno with TOF SMS high resolution, if we can screen new chemicals in this human milk. Therefore, a suggestion to the research community would be that the research community in a country could ask to the focal point, the Stockholm focal point, and said, could we make a research project with the human milk study? Yeah, you have to do the human milk study. If we do it a little bit bigger, you will get much more data out of it. Yeah, but also for the human milk, we have the same problem. Yeah, we monitor the PCBs, the DDT, which will decrease. Yeah, we have now the PBDE, which increased from 1975 up to here early 2000, but they are also now decreasing. So also there we have to take care that not the policymakers think all things are okay. We should somehow include also new compounds. And there is just this week a publication from Schlumpf et al. At Chemosphere. She's analyzing just these consumer toxics in human milk. This means the masks and the sun blockers. Yeah. So combining it with this would be quite interesting and could be used then for awareness raising. Okay. We come to the first compound. These are the PBDEs as new POPs. And this was actually the work of my last 8 months. The evaluation to how PBDEs can be controlled under the Stockholm Convention. We had a consultancy for the Stockholm Secretariat, together with Alan Watson. He's an engineer, and Tom Webster from Boston University of School. He's a toxicologist. Why was there the consultancy? The consultancy was about PBDE was coming into Stockholm Convention, and one problem was that the PBDE currently are in the recycling flow, and the Stockholm Convention excluded this recycling. And the question for the consultancy was, how reasonable it is to exclude the recycling sector, or if it can be included again. What we have done is, in parallel to our consultancy, we presented the Stockholm Convention activities to the POPs research community in 4 large POPs meetings. This means the BFR 2010, the Dioxin 2010, the CTEC Asia, and now also here, to make the science community more aware on the challenges and the knowledge gaps of the Stockholm Convention in respect to the PBDE, possibly get an input from the science community, you will see why, and maybe stimulate some research by highlighting where information is needed in respect to PBDE. This is what I'm doing here in this presentation. The PBDEs which are listed in the Stockholm Convention now are the commercial penta-BDE and the commercial octa-BDE. And from the commercial octa-BDE, actually only the hexa-BDE and the hepta-BDE homologues are listed. The octa-BDE is not a POP from the Stockholm Convention, also it's of course in the octa-BDE mixture, because it don't possess the POPs property. And also the commercial deca-BDE and nona-BDE are not in the Stockholm Convention, because they have not the POPs properties which we have defined. Yeah, I told you in the first slide, yeah, as a very specific definition which were not met from the octa-BDE to the deca-BDE. But also with the PBDEs, like for the other old POPs, there is no production anymore. The last production for PBDE was stopped in 2004 in the US. So the main challenge for the PBDEs was the identification and the management of the PBDEs in the recycling sector, and the treatment and the recycling of the waste. And these are large waste flows. These are the electronics, building materials, polyurethane foam from mattresses or from cars. And by including the PBDE in the Stockholm Convention, there was the last question if these kind of recycling flows will be impacted, and for example that you will have to stop the recycling of plastic from electronic waste. And because of that risk, finally in the Conference of Parties, the parties decided that the recycling flow is exempted from the Stockholm Convention, and actually what means that the only relevant part where we at the moment phase out the PBDEs were exempted. Yeah? And this exemption of the relevant part, of course, then had other parties which said, if you now exclude the most relevant parts where we have the PBDE in, what is the meaning? Yeah? So the convention is not working. Yeah? And this was the reason then the Stockholm Secretariat made this consultancy to evaluate how much the recycling flow would be impacted. This means the size of the problem, the types and quantities of the articles in use, and the recycling articles containing PBDE, the extent of recycling of the PBDE containing articles, then the methods to identify the presence and levels of PBDE in the recycling. Yeah? You can imagine what kind of challenge you have to identify if this television contains PBDE which is listed, or if this television don't contain it. You cannot analyze each single television set or each single mattresses. Then options for environmentally sound disposal of the PBDE containing waste, the identification of remediation methods for contaminated sites, and this information were then compiled from us, together with assessment of the possible health and environmental impact of recycling articles containing PBDEs. the identification of best available technology and best environmental practice for the recycling of PVDEs, and the review of long-term environmental desirability of this recycling. And for many of these topics which I have just listed, there is of course information from the scientific community. However, for a wide range of these topics, there is a research need. And the key speaker of the BFR 2010, Professor Richard Hall, highlighted that he was wondering why there was completely no contribution in the whole BFR conference on the material flow. Yeah? Because currently more than 90% of the PVDE are in the material flow, yeah, and they are in the landfills. But what science is doing is we are researching here in the environmental transport, in the exposure, and only rare papers are about products, are about recycling, are about the reservoirs in landfills, are about the thermal treatment, where finally all the products containing the PVDE end up. And while for the old POPs we know, okay, this is the most relevant pathway for exposure. Today we know that for the PVDE and for other new POPs, the main pathway to the humans are indoor, are in the car. Yeah? So therefore this area becomes much more important. And also for the dioxin conference, there was more or less 100, 150 papers about this area, but only maybe 1 or 2 papers related to this area. So therefore, a question to the research community: what is the flow of PVDE in recycled materials? What articles are contaminated, and what are the risks to human and the environment? Actually, in the last 10 years, only 5 papers were published. I just showed 2 studies. One is the PVDE in videotapes in Japan. So all videotapes they analyzed contained PVDE and other BFRs, but in a very low amount. So this was just made from recycled material in China and in Korea. Then another study on children toys in South China from Chen et al. 2009, and he found more or less that in all hard plastic toys, PVDEs are included and other brominated flame retardants, yeah, and that they were made from partly from recycled plastic. Yeah, these 5 studies show that the recycling flow of PVDE and BFR containing plastics seems largely uncontrolled, and increase here the environmental and the health risk in an uncontrolled manner. These are the data from the Chang study, and this is here for hard plastic, where you see that in basically in all samples they find PVDE in different concentrations. So I think that this is a quite important task for the research community to screen on contaminant levels of PVDE and other critical pollutants in the recycling flow and recycled products, and to assess the related human exposure and the final sinks. Then there is only one study which assessed the human exposure of recycling of polyurethane foam. Polyurethane foam is recycled in the US. What are they doing? They use it then for backing of carpets. And what we see here is the PVD content in the serum lipid, the control in America here, but you know that America has about an order of magnitude higher levels of PVDE than, for example, Europe or Brazil. And when you look then to the contamination here of the polyurethane, that's really unfortunate, polyurethane recyclers, you see that they are 1 order of magnitude up, and also the carpet installers, which finally put then the carpet, have also an order of magnitude higher contamination of PVDEs. And of course there is the question, how is this recycling in other countries? Yeah, there is an urgent need of more studies of carpet recycling in the US. Yeah, but there's also the question here for Brazil: what are you doing with the polyurethane foam? Yeah, are you recycling it or other PVD containing materials? And how are the levels of consumer exposure of the articles made from these recycling materials? Yeah, especially when you look, for example, to carpets. Yeah, 25% of your apartment can be covered by this. You have a very high surface. Yeah, so quite high exposure possibility. And the other part is not recycling, is the end of life. End of life treatment of PBDE containing materials or flame retardant materials. End of life in, for example, for printed circuit boards in the metal industry, yeah, plastics in cement plants or incinerators. And we found a huge assessment gap. Even for industrial countries, no PBDE or BFR or brominated dioxin data for smelters processing printed circuit boards. And these are thousands of tons of brominated flame retardants which are coming into these smelters. Also no data for antimony smelters, no data for cement plants or incinerators. Yeah. And in the last 2 years there are now some studies for incinerators for PBDEs. And when we think about different countries, these data, for example, come then from America. Yeah, we don't have data from developing countries or transition countries on these studies, but they have different technologies, of course. Yeah, so when you get the data then from a US metal plant, you cannot actually use them then also for Brazil or for another country. And what one big hole we discovered is the risk assessment for chemicals, because the risk assessment for chemicals, they largely focus on products and for the use phase. This is actually required from the producer to do a risk assessment. The risk assessment for the end of life phase and also for the end of life for the recycling is more or less not developed. However, the development of robust risk assessment scenarios for recycling and end of life are becoming more relevant, considering that material recycling and closed material cycles are globally increasing. So here I see a very big task for the research community. And when we come to the end of life, that's the landfills. We see that it's estimated that about 80% of all PBDEs which have been produced finally end up in landfills. So we have produced about 1.4 million tons of PBDEs up to now. This means in landfills we have around 1 million tons. The largest amount is here highly brominated PBDEs. From the 1.4 million tons, about 1 million ton is DKBDE. The question is, what is the fate in future? Yeah, and this was a good paper from Dioxin Conference 2010 from Dan and Schäfer et al. She modeled what will happen with the DKBDEs and the PBDEs in landfills in respect to debromination. Yeah, landfills are anaerobic, so when you have DK, you can assume that over time the DKBDE is debrominated. And here she modeled, you see here, starting from 1980, the PBDE come into the landfills. She was positive and she thought that 2010 will be the top, but actually we have a high production of DKBDE, so this will be considerably later. And then she modeled with some kinetics of debromination, and here then we think about perspectives of decades and centuries of PBDE debromination in landfills. And the actual question is, what will happen with the PBDE release over this time span? Yeah, we have about 5 studies in the world also on release of flame retardants from landfills. We find them in the leachates, we find them in the groundwaters around the landfills. Good study from Dan and Schäfer about Canada, that around all the landfills she have investigated, you have increased levels around in the air, in the soil, and in the leachates. So that's an interesting task for the research community. Then the largest producer and user was the US, production until 2004. We have here the largest reservoir. So the question is here, what is the substance flow of the electronic waste and, for example, PVD containing cars from the US, but also, of course, from other countries? Yeah, because finally this is the way these chemicals will be distributed. We know it for electronic waste. Electronic waste is mainly exported to China up to 2006. Now they have a legislation. Now much of the electronic waste is diverted to India, Pakistan, Vietnam, Philippines, but also to African countries. The question is, how is the recycling and the live treatment here? There are several papers on that. This is the way finally there the electronic waste, including the PVDs, are recycled. Yeah, open burning just to get the heavy metals, copper and so on. And this is how Wuyu looks like. That's one of the two major e-waste recycling cities in China. This is all ashes from electronic waste. Yeah, and here just nearby the river. So in this area you cannot more or less live anymore. Yeah, so drinking water they gave up 15 years ago. They have drinking water from outside. Yeah, coming by trucks. And the question is then here, what is the risk assessment? So here it's clear. Yeah, this have to be forbidden. But also, of course, here the risk assessment cannot come then for the PVD or for the brominated flame retardants, but you have then to consider all the compounds. This is just what the colleague said about the drinking water. So the same question we have also for recycling and also for the thermal treatments. Yeah. And currently, when you do risk assessment, normally you do it for single compounds. Yeah. Also for occupational exposure. So that's also for the research community. Yeah. Here a list where I think interesting areas for the research community: risk assessment of recycling scenarios and end-of-life treatments in industrial and developing countries, considering multiple pollutants; global substance flow analysis of PBDE and other compounds in products and recycling; PBDE contaminated sites from production, application and end-of-life treatment; external cost estimation of harm caused by these pollutants to humans and biota. Because one problem which we will face is that, okay, the company said, yeah, if you stop now this recycling or if you take out this will be losses in money. Yeah. And if you don't have very good arguments against that, and one of the best arguments against it is when you can make also an external cost estimate, it will be difficult to make changes. And interesting task would be life cycle assessment of PBD alternatives, other flame retardant alternative technologies, which I will highlight also for other compounds. Yeah, and here already GAPS and others are screening for other brominated flame retardants and their toxicity. But finally, also these chemicals will go through the whole life cycle which I showed at the moment. Yeah, and they will have the same challenges, even if they are now less toxic. When you have brominated aromatic compound, finally in thermal treatment, you have difficulties. Okay, now we come to the second new pop, that's PFOS as first fluorinated new pops. And here I would like to highlight the assessment of local pollution by PFOS and the assessment of PFOS alternatives. And one thing in the beginning of the presentation which I will highlight, that otherwise we have similar challenges and questions and research tasks like for the PBD. This I will now not address here for PFOS. Yeah? But the same what I just said for the PBDE is valid for PFOS and the recycling or the substance flow of them. Okay, we have an estimated global production of PFOS between 1970 to 2010. That's about 100,000 tons in products and about 26,500 tons in production waste during the production of PFOS. In total we have 122,000 tons. So our question is, where has all the PFOS gone? And during this study, looking where have all the PFOS gone, we should also track other PFCs at the same time and look to the substitutes. So This here are the application data of PFOS in the EU in 2000. Yeah? Here the consuming industry used products, and you see that nearly 50% of PFOS went into carpets and textile treatment. 30% went into paper and board treatment, and just 20% are performance chemicals in industries. And then we have the firefighting foams, where you will see later on why they are also quite interesting, and especially their use. Yeah? But also here you see, like with the PBDE, a large part of it is in the consumer products, which we have in daily life, yeah? And which finally end up in landfills. And the difference between the fluorinated compounds and the chlorinated and the brominated compounds is that when we look to the brominated and the chlorinated compounds in time perspective of 10 years or a century, it will degrade. Yeah? When we look to the perfluorinated compounds, we can look into time perspectives of 100 years, 1,000 years, 10,000 years, 100,000 years. They will not degrade. So in the environment there is no known degradation of PFOS, for example. Yeah? This is the difference between these two chemical groups, which have to be kept in mind. Okay. Also here, the research community is mainly now looking to environmental transport, exposure routes. It's interesting because it is different, completely different, because you have PFOS in the water. Yeah, so you have here drinking water and also then directly from water into fish. Yeah, but we have the same question here for the ocean source and where actually the PFOS stocks are. Yeah. Okay. So my suggestion would be to do research along the life cycle of PFOS, PFOA. And the two case studies I selected for this afternoon is one of a case of PFOS producer we just presented at the Dioxin 2010, the 3M, the primary producer of PFOS. And then I will present a case study on screening in a German city where PFOS have been used, and a screening of the German rivers. And you will see the whole thing is very relevant for water, especially also for groundwater. Okay, the 3M was the primary producer, and it's based here in Minnesota, near the Great Lakes. 3M produced in several plants in the US. One is this cotton-proof plant, where I will show some data. And here, in addition to PFOS, PFOA, other PFCs were released during production, but significant amounts of PFC waste were generated and were stored. In the first slide of the PFCs, you have seen that from the 120,000 tons, about 20,000 tons were waste during production. So it's a great study from Fardine Oliai. She worked in the environmental agency of Minnesota, and she did a comprehensive monitoring study of this plant. Yeah? Here she looked to the waste stream, she looked to the ambient environment. Here she looked to the landfills, to the wastewater treatment plants, in the landfills, to the gases, to the leachates, to the groundwater. Here to the sludges and the effluents, and also to the Mississippi River water sediments and the fishes. Quite comprehensive, the substance flow for this producer, and also she looked then to exposure, drinking water, and the fishes in the Mississippi. The PFC waste from 50 years of production still remain in the landfills. The landfills are leaching, going into the groundwater, into the Mississippi. Also, the PFC waste from the current production of the 3M plant is deposited in industrial landfills. And here I really have to ask the authority, when you think about time perspectives of persistence of hundreds and thousands of years, how can you bring this kind of compound in a landfill, even if it's managed at the moment? Yeah, within the next, let's say, 50, 100 years, the kind of liners and water treatment will will fail, yeah, and finally things will come into the environment. We have here now for this plant a fish advisory down to about 80 kilometers down the Mississippi, and similar studies like the one which is done for the 3M, I think would be interesting for all PFOS and PFC producers. The question is what will be with the future fate of the 100,000 of tons of PFC waste in these landfills. So that's just one example. Other producers will have most probably the same problem. Yeah, America is quite advanced and actually would have incinerators, but maybe one reason not to incinerate it is first, it is a real challenge to incinerate PFCs, and often you have wet sludges as a waste, which are very expensive to destroy. Yeah. So actually, I don't understand why 3M have not destroyed this waste, but I think that this is the reason. Yeah. And therefore, for other producers in the world, it might be similar. I know, for example, for Japan, of course, they have their incinerators. Yeah. Also in Europe, Belgium, they have their incinerators. Yeah. But when you go to China, for example, I know for their PFC producer, they don't have an incinerator. Okay. I don't know if you have a PFC producer in Brazil and how is the waste management of it. Yeah. So where have all the PFCs gone? Finally, they end up in the ocean. That's a nice study from Yamashita et al. Yeah, you see here, Europe and America, we have already partly polluted our Atlantic. Also, China and Japan is about to pollute here the ocean. The concentration is nearly, it's up to 1 nanogram per liter, yeah, which is quite high for ocean. And up to now, it is estimated that just 230 to 2,000 tons of PFOS are now in the ocean. Yeah, this means 99% are still to come. Okay, the second case study, it's about Düsseldorf. And you see, you have the most famous carnival here in Rio, but also we in Germany have our carnival, and Düsseldorf is one of the major cities for carnival, and they have also very good beer. I don't know if the reason is the beer that they have that good carnival or other way around. But what I know is that several of the beer breweries stopped using groundwater in the last 20 years because of chlorinated AOX. Yeah, they had to use to switch to normal tap water. And so the last 20 years they did much remediation in Düsseldorf, especially for the groundwater, and they would be now close that for the chlorinated compounds they can use again the groundwater for making their beer, but now new chemicals come. In Germany we had in 2006 a large environmental scandal. Our largest drinking water reservoir was polluted by PFOS PFOA. This will be the next story, and because of that, German cities started to screen PFCs in 2007. So that was the start for Düsseldorf. The first samples they analyzed already here, the red one, okay, this means in the groundwater some PFCs here, in the groundwater PFCs. This was February 2007. End of 2007 they already have found 3 PFOS contaminated sites, groundwater in Düsseldorf. And this is now early 2010, where Düsseldorf have discovered within these 2 years about 9 PFOS contaminated sites, the groundwater. So, this is why I said we also have to look to the applications. These are contaminated sites from chromium plating where you use PFOS. Go down here, it goes down into the groundwater. This here is the Rhine area. Here you have the drinking water well, so they are sucking. Anyway, the PFOS move direction to the Rhine River. This is from application of firefighting foam, also application of firefighting foams. Here, firefighting foams, the AFF foams contain up to 1% of PFOS, so therefore if you have a major fire, or if you have fire practice, over the time you will get contaminated sites from PFOS. And this very large site, that's the airport. Yeah? And the airport have several PFOS contamination sources. One is from firefighting practice, because at each airport you have firefighting practice, and because of the airplane fires, this is strong hydrocarbon fires. Normally you use AFFF foam. Yeah. Additionally, you use PFOS, or you use PFOS compounds in anti-icing for the airplanes, so this is not a problem in Rio. And the hydraulic fluids from airplanes contain PFOS. So more or less all airports in the world will have some PFOS contamination. Yeah? There's up to now no paper out. Yeah? Also here for this, at the moment, Düsseldorf City don't talk about, but it is already clear in Europe all major airports are screened at the moment. Yeah? So for your research community, you can just start at the airports. And this is interesting. The red ones are the PFOS contaminated sites, and the yellow ones are those contaminated with chlorinated organics. Yeah, over the last 30 years, where Düsseldorf made much effort to do a remediation. But when you add all this together, you see that let's say 30% of the whole area of Düsseldorf somehow in the groundwater is polluted. Yeah. And I think this is one of the best investigated cities in this respect, and could be really a standard approach, yeah, for other cities into their groundwater. And they also look not only to the fluorinated compounds in their groundwater and the chlorinated hydrocarbons, they also looked into PTX, PAHs, pesticides, and the others. The problem with the AOX and the PFCs is that they are quite mobile. Yeah. So when you have a contaminated site with PAHs, normally it just stays at the place. Yeah. Here is how long is the bloom length? Yeah, below the city of Düsseldorf. Yeah. And so you see with PFCs that within this, for example, this is the PFC case which happened in 2001. Yeah, and it needed about 10 years that it moved 400 meters. Yeah. And now I come to another approach, how you can screen a country for PFC pollution. What the research group of Bonn University did for Germany, that's the Rhine River. The Rhine River comes here from Switzerland, flows through whole Germany, finally end up in the Netherlands. Yes. And they have screened the whole Rhine River for PFOS and PFOA and looked to all the tributary. And here in the area of the Ruhr, they have found a quite high concentration. Then they tracked the Ruhr up to the Möhne, and finally they found that in this small creek they had huge concentration of PFOS and PFOA, yeah, up to 40 microgram per liter, not very industrial. And the reason for this was that agricultural areas were treated with sludge. Yeah, so a company imported sludge from the Netherlands to Germany, to a small German company. They were waste traders, so that was actually okay. Then they mixed it with soil and sludges and finally sold it to the farmers. Very easy. You can make good money. And unfortunately, they put it directly here in an area which is just above the highest German drinking water reservoir. That's the Möhne Lake. And here, this is Essen, Duisburg, Dortmund. Here you have about 5 million people, and they get drinking water from the Ruhr area. So this was really a catastrophe, but a very interesting case. And the case is so interesting that because then, of course, the authorities had to do a detailed evaluation And finally, they found out it is not only these contaminated sites, but also that in this area you have about 37 industries which are using PFOS and PFCs, which finally come into the river and contribute here to the drinking water reservoir. Yeah? And I think a documentation of this case would be really an interesting case study then for other countries to do similar assessments, at least for the industries and to the waterways. So a summary for task for the research. Over the last 40 years, large groundwater drinking water pollution around PFOS, PFC producers and users. Research, find and assess these sites. Important to assess here human exposure around these sites. Exposure pathways are drinking water, the fishes and the plants and the kettles. That was especially interesting for Düsseldorf, yeah, where you see when you have the PFOS in the drinking water, yeah, it goes then finally in the plant, yeah, in the apples. And there is now stop for gardening in this area in Düsseldorf. Then currently there are nearly no established limit values, for example, for drinking water. For drinking water, there is only the German drinking water guideline, which had to be established because of that case where 5 million of people had PFOS and PFOA in their drinking water. And this drinking water guideline is much too high. Yeah, this is really unfortunate because when you see presentation, people are citing this German drinking water legislation. Yeah, but this is, in my opinion, not really developed on risk assessment. Okay, and interesting task is to do a substance flow analysis for a country. There is only one. This is for Switzerland. So you see here the PFOS in the production, in the waste management, and finally in the environment. And here for Switzerland you see where are the large stocks. The large stocks are here in the firefighting foams. Still here some in the service life. Then we have here a relatively large stock on landfills. Also Switzerland have 100% combustion capacity. So this for all other countries will be much higher. This will probably be the highest. And some then already here in the hydrosphere. Yeah, and therefore also here we are, like for the PBDE, finally at the landfills. Yeah, the largest part of PFOS are currently in the landfills, and there are some studies from Sweden, Germany, which shows that in leachates of landfills you have the PFCs in different concentrations. So it's interesting to screen here landfills and assess their impact, yeah, to the area, especially when you have a river nearby. And some other tasks for the research community. One problem for the PF is that there are only a few analytical standard procedures established for water and wastewater, but for most other matrices currently there's no standard method available. We have to develop them, and one large problem here is the analysis of PFOS precursors, and for example of PFOS contained in carpets or in paper, because they are directly then linked here, chemically linked to the textile. Yeah, how to do a quantitative analysis of PFOS here? Yeah, because actually you would need a destructive step like oxidation with something. Yeah, task to do. And a major activity in the Stockholm Convention for PFOS is the substitution of PFOS. Yeah, the main substitution for PFOS are other fluorinated compounds, mainly with shorter chain lengths, C6 chain length, C4, or mono and polyfluorinated ethers, or fluorinated oxytans, other fluorinated polymers. For most of these alternatives, there are very weak or no toxicity data, so that's a large task. One, of course, for the industry, for example, under the European REACH regulation, but also for research community to develop comprehensive toxicity data. And for more or less all of these alternatives, there are no trace analysis. So also this is a nice task for the research community. And interesting to look to the degradation mechanism, because while for PFOS and PFOA, which are perfluorinated, no degradation is observed in the environment, but with the substitutes, normally the industry has part of polyfluorinated moiety in the compounds, and then you have carbon with hydrogen, and of course this will then degrade in the environment. Yeah, but how fast or to what compounds they are degrading, that's a very interesting research area for the science community. And what is the toxicity of these degradation products? Then we have alternatives, hydrocarbons and siloxanes for the fluorinated compounds. Here, especially for the siloxanes, is a very nice new research field. There was in 2009 the first research conference on siloxanes, and also here the question of degradation products of silicone polymers. Yeah. Then, because you are mainly interested in fishes and biota, I have two slides here which also show that, of course, here the PFCs is an interesting research topic. You see, while here for the PCBs and the DDTs it's decreasing. These are pops in melon-headed whales stranded along the coast of Japan. Yeah. Here for the fluorinated compounds you see a decrease between whales catched in 1982, 2001 and 2006. And interesting, when you look then to the distribution of the fluorinated chemicals, you see that in 1982 really the PFOS and the PFOSA, this is a precursor of PFOS, were up to 80% of the fluorinated compounds in the whales, and over the last 20 years it moved that today just about 50% come from PFOS compounds, and here the fluorinated carboxy acids strongly increase. Yeah? And this is partly also from substitutes, so this will further increase. And PFOS and PFOA seems to be very relevant for our industrial society. One large challenge we have today is the male reproduction. The sperm quality over the last years in industrial countries is decreasing. Especially Denmark has a very strong research. And here you see the results of a study of 105 young Danish men. They were analyzed for their serum levels of PFOS, PFOA, and then they made 3 groups: the lower contaminated and middle contaminated, higher contaminated group. And you see that the sperm quality of, and this is background level, these are then here not people which work in a PFOS factory, yeah? These are just like you and me. No. You see that the sperm quality was decreased by more than 50% when you compare here the lowest contaminated group with the highest contaminated group, and this is really striking. And this is the only study up to now to sperm quality. Yeah. So I think that here, and this is just 105 people. Yeah. So here there is a much research need that other countries repeat this study. We should care that not the wrong foam go into the right stuff, because in Düsseldorf they cannot use the groundwater for their beer for the next 20 years. Huh? And we have here PFOS and PFCs as a first globally addressed chemical class, which has the final sink in the water. Yeah. I think especially now the research community should pick on that. Yeah. See here the problems, and then we have to add what other compound classes have to be addressed, and maybe we can use the Stockholm Convention here also as a tool. New pop, which is now listed in the Stockholm Convention, are the hexachlorocyclohexanes and lindane, which is now called a new pop, but which is one of the oldest pesticides we used. And the question I want to address here in the presentation or highlight as a key topic for the implementation of the Stockholm are the 4 to 7 million tons of waste from HCH production. So HCH and lindane were one of the most extensively used organochloride pesticides in the past. We very good understand the distribution
in the world, pollution in the atmosphere. We do modeling with McLeod, who is now in Stockholm Convention, in Stockholm University. But what most people are not aware of is the problem of the waste from production. When you produce methane, you chlorinate benzene, and in the chlorination of benzene you get about 15% of the gamma isomer. And the gamma isomer is the only active ingredient of the HCH. So therefore in production of lindane you have 85% of waste. And in the 40s and 50s the gamma isomer were applied together with all the waste isomers to the agricultural fields. But in industrial countries we very early stopped it because we could not eat the potatoes and we could not eat the drink because the other HCH, they have a very particular taste. And therefore already in the 40s, already in the 50s we started to separate lindane from the HCH waste isomer. And here you see a factory in France close to the Swiss border. That's the Rhine River. And what you see here, this is not salt, this is HCH waste. Yeah, 10,000s of tons, and actually the person who made this figure, this picture, this was the prosecutor. Yeah, it was in 1972, France, and at that time, this means the early 70s, also industrial countries just started to manage these kind of wastes. So the mismanagement of this waste generated one of the largest pop stockpiles which we have at the moment. So this is Germany, East Germany, this is not snow. This is also HCH waste dump in the 50s, 60s in East Germany. And actually we used the HCH at that time as bottom liner for our chemical landfills because HCH was relatively water, or thought that it's water, less water soluble than the other waste they had. But actually, HCH has water solubility between 1 milligram and 10 milligram, depending on the isomers you look at. So just in one landfill here in Bitterfeld, we have about 100,000 tons of HCH waste deposited. And on top of it, we put then other chemical waste, and finally put some soil on it. The question is, what happened with it and what is happening now with it? This is picture from India, from the last lindane production near Lucknow. Here in this area, or from this factory, about 60,000 tons of HCH waste is deposited. And in total, when you estimate, and you can easily estimate it, because you just have to look to the total lindane production. The total lindane production was about 600,000 tons. And for each ton of lindane, you have about 10 tons of waste. Yeah, and then you can estimate that you have about 4 to 7 million tons of HCH waste deposited. And here, the countries with the red spots, these are the countries which have produced. You see the largest producer at that time were Europe. Here, Germany, we have the biggest spot. Yeah, but also France, Spain, Romania. And in South America, there were two producing countries. One was Brazil and the other is Argentina. So I just want to show from 3 facilities what the current situation is there in a very short slide. First, start with Rio. The POPs residues in soil at the Cidade dos Meninos. You see here we are also talking about ppm levels. So when you are close to old industries, you are not thinking about picogram and nanogram. Yeah? You are talking about microgram and milligrams and kilograms. And this is a study from Professor Asmus. So she analyzed also here the eggs. And you see also in the eggs, you have beta HCH at the ppm level. Yeah? And also DDT, DDE and DDT in the ppm level in the egg. And when you then do a risk assessment, exposure dose calculation for the excess risk, for example, for non-carcinogenic effects, you see that here the exposure dose compared to the reference dose are several thousands above the acceptable dose. Yeah. So when we look to the old POPs, these old production sites and the releases from the old production sites and the landfill sites, these are real interesting issues. But they are not highlighted in the Stockholm Convention. Just mentioned in one paragraph in Article 6, where it said, okay, you should look to your POPs contaminated sites, and if you do the remediation, then you should do it in a proper way. Yeah? The main reason that this is so soft is that if there would be a much stronger article on it, probably countries would not have signed the convention. So we come to a second place, that's just a Bitterfeld, where you saw the landfill. And here the data, what you see is HCH in fish, in trace, in the river Mulde, which is close to the landfill. The landfill were finalized in the 1980s, and we had decreasing levels in the fish from middle 1990s down to 99. But then when we had the flood in 2002, the large flood in Europe, the values jumped up. Yeah, and here this is the levels where you can, or the beta HCH, consume the fish way above the levels for the Mulde River. And the Mulde River is going to the Elbe River. You see here again the regulatory limit for beta HCH in fish. This is the river Elbe before the Bitterfeld area, and this is the river Elbe after the Mulde River comes into the river Elbe. You see also this large Elbe River then went far above the levels in the fish. And these are the same fish caught in Hamburg. Hamburg is 300 kilometers downstream of Bitterfeld, and you see, oh, here the values are much higher. Why? Because in Hamburg we have the second HCH factory. Yeah? So also in Hamburg you get an impact from an old HCH factory and old deposits into the Elbe River. And for Hamburg, I want to show you two pictures. For the Hamburg factory, this was the old factory, was stopped in 1984. And this is probably the best investigated ground under a factory. The Hamburg factory, what did they do? They did not deposit all the HCH waste. They already started in the 50s to recycle the HCH waste. Because, of course, you have the 70% chlorine. Yeah? So what did they do? They produced from HCH, by a thermal process, they produced tri and tetrachlorobenzene, and this tri and tetrachlorobenzene they used for production of other organochlorines. They produced 2,4,5-T and some other pesticides out of it. And when you look here in the ground of this factory, you see now under the factory about 260 tons of HCH, 550 tons of chlorobenzenes, and about 6 kilogram TEQ from the dioxins. And this is in the middle of Hamburg. Yeah? And so then in 1990s, Hamburg City, or in the company, this was then mainly paid by the company, they built a wall around the whole factory, and this wall went down to 50 meters deep. Yeah? That is about 1,000 tons of POPs don't reach into the groundwater of Hamburg. And, very interesting figure for Hamburg, during this process, the decomposition of HCH to chlorobenzene, you produce huge amounts of dioxins. And here in these samples from the decomposition process, you had dioxins in percent range. Yeah? And TEQ in very high ppm range. And so the total dioxin which is today deposited in the landfills of Hamburg, yeah, there are here 4 landfills in Hamburg, and you see on one landfill here as well, you have deposited 270 kilogram TEQ. Just to compare it to global dioxin inventory, today when you accumulate all dioxin inventories from the whole world, you come to about 50 kilogram TEQ. Yeah? So you see that just in this landfill is the today emission of 5 times of the global dioxin inventory. Yeah? To give you a perspective, and in total they have about, in Hamburg, deposited 370-80 kilogram, also in the middle of Hamburg. Yeah? And when you add the dioxins which they deposited outside of Hamburg, you come to nearly 1 ton of TEQ from one factory. Okay, that was a very soft introduction into the topic of unintentionally formed POPs. This is, for example, dioxins. This means intentionally formed POPs are those which are produced by industry, like DDT, and unintentionally formed is which are formed as a byproduct here from a chemical process or from an incinerator. When you look what which compounds are listed, you see that the Stockholm Convention today with dioxins, furans, unintentionally PCBs, like we said in the paint from probably from the Korean station and maybe also here from the Chilean station. We have unintentionally PCB in paints, yeah, or hexachlorobenzene and pentachlorobenzene also are formed in some processes unintentionally. Then the UNECE protocol suggests the listing of hexachlorobutadiene, octachlorostyrene, and they already have included the polyaromatic hydrocarbons, unintentionally formed POPs. And there is the paper from Vandenberg, this is the WHO TEF advisory group. They said that other unintentionally POPs which would be important to at least be evaluated for the TEF concept are brominated dioxins, brominated furans, the mixed halogenated. Yeah, they are at the moment not included in any regulation. And of course there are then others. Yeah, you can chlorinated polyaromatic hydrocarbons, brominated polyaromatic hydrocarbons. The question is, which one are really relevant? I mean, also relevant for human exposure. Yeah? And we see from studies of dust, for example, in Japan today, when you analyze the house dust in Japan, about 50% of the TEQ come from brominated furan, and much less come from the chlorinated compounds. Yeah? And the same, very active, is the UK Food Agency. When they analyze today their fish samples and our food samples, they see a contribution of the brominated dioxins up to 30% of the TEQ. Yeah? But here it's a very interesting task for the research to demonstrate and to decide which of the unintentionally POPs are actually necessary to address, because if you decide, then the analysis becomes very expensive and much work. So you really have to decide what kind of compound it is. So what is actually done for unintentionally POPs in the Stockholm Convention? But these inventories are then inventories done for actual year, like then if you do today inventory and you do an inventory for 2009 and just for this year. Then promote substitution, for example, phase out PVC in hospitals that by incineration we don't produce so much dioxins in hospital incinerators. And then promote best available technologies for incinerators, metal plants and so on. So today the Stockholm Convention mainly focuses on the thermal sources, yeah, and the reduction from the thermal sources. And inventory, they just make inventories for the year we are looking at the dioxins. So today, not much is looked into the topic of the reservoirs, and also not much is done with dioxins in products or in some productions. But when you look into sediment cores, and this is a sediment core here from Switzerland, this is another sediment core from Germany, like Professor Hartmann, and you look to the time frame when here the red one is the dioxin appeared and disappeared to it, you see that we have a peak here in the 60s and 70s, and already at the end of the 70s we were back to the levels of the 40s, and actually just at that time we start this reduction of dioxins. This means at that time nobody looked about dioxins except of the industries in their products, yeah. And today with the reduction of incinerators and so on, yeah, this huge emission is not addressed and was not addressed. So what was the reason for this high impact of dioxins in history? There is only one
historic dioxin inventory. That's from Japan. And it is this one from Professor Masunaga from 1980. He analyzed all pesticides in Japan. He analyzed several PCPs and CNP samples. These are pesticides which Japanese used in their rice fields. And what he found when he calculated the concentration of dioxins he found in these old PCPs and the application rates, he found that by the application of PCPs and CNPs in the rice fields, in Japan you had here in the 60s an annual emission to the environment of 50 kilogram TEQ, just for Japan. Yeah? And when you would look today in sediment cores in Japan, you would also see here this trend from the past, yeah? The same we observed in Europe. Yeah? And these are the dioxins from incineration, yeah? Much lower compared here to the PCP application. What you have to know is that here, this 8 kilogram TEQ in Japan from incineration was by far the highest impact from any countries, because in the 80s Japan had about 50% of the whole incineration capacity of the world. Yeah? So today when you look in the Brazilian inventory for incinerators, I think we will not come to 100 grams. Yeah? So these are completely in other orders of magnitude we are looking for. So I think this historic dioxin inventories, this would be a very interesting task for research. Yeah? To understand the fate of dioxin in the countries or in the river. Yeah? Also then for the modelers. And the question, are these dioxins which were applied in history in Japan, are they relevant for today? So here you see the dioxin load which were applied to rice fields in the Tokyo basin. Yeah, this mean which finally from precipitation would end up in the Tokyo basin. You see the dioxin load to the basin, and this is kilogram per year. Here in the 50s were 4 tons, yeah, 3 tons, and this is not on TEQ base. Yeah, this is on total dioxin. And this morning Jana mentioned that in the UK today we have about 0.6 kilogram of dioxins to the UK soil total, and this was also not TEQ. Yeah? Also you can add here a perspective and compare Japan with also fucking higher compared to the UK of today. And interesting is here the deposition today in the sediment of Tokyo Bay. Yeah? These are the dioxin coming from PCP in the sediment in 1975 up to 2000, and we see that the aging from the soil in Japan, yeah, was peaked a little bit later than the application rate, yeah, but then went down by about 50%, but then here it levels off, and it very slowly degrades into the Tokyo basin. And I choose the second example. This is an example of a total substance flow of dioxins from a PCP and chloralkali factory in Finland. I choose this example first because it's the only substance flow for a factory for dioxins, and second that I know it's interesting maybe for Chile, since you also had a PCP factory. So they produced PCP between 1940 to 1984, and during this time they discharged about 28 kilogram TEQ into the river, Kymi River. And there is a large remediation project in Finland ongoing for this river, and they have divided 3 sections. This is the section of the river which is close to the factory. Today only about 10% of the dioxins are in these sediments close to the factory. 12.8 kilogram of TEQ have moved over the whole river, about 50 kilometers, till the Gulf of Finland, and already half of it is discharged into the Gulf of Finland. Yeah. And they also did a risk assessment for it to decide what kind of remediation to do, because then to do a remediation of a river of 50 kilometers, that's very expensive, and for the Gulf of Finland this is already gone. You cannot do a remediation. There's too large amount of sediments. At the same time, this factory which had chloralkali, they also emitted high amounts of mercury into the river. And when they did a risk assessment, also these dioxins are in the high kilogram range, they calculated that even the higher risks come from mercury. And from mercury, you see also they made a total budget for the river. Today, close to the factory, still only 140 kilograms are deposited in sediments. Over the river, about 2.6 tons of mercury are in the sediments of this chloralkali factory. And just from this one factory, you have emitted 28 tons into the Gulf of Finland, Sea, the Baltic Sea. So also here, I think a very interesting task to look to old factories or new factories, which we saw yesterday from Spain. The other old factories from organochlorine, where you also see the concentration in the sediments. And we see today the discharge of these factories of the brominated compounds. Same story, just in bromine. So in the last 20 years, actually, then researchers have not looked very much to dioxins in organochlorine chemicals and in pesticides. And unfortunately, also in the toolkit, not many of these are listed. Just the old one like 2,4,5-P and PCP, which are not produced anymore. So therefore, we had a PhD thesis, or we have just finished a PhD thesis in Australia, and we have looked into dioxins in pesticides in Australia, and we have found high levels of dioxins. So first, we have found in all pesticides analyzed, we have found dioxins. Even in those pesticides which have not included chlorine. Very interesting. But they were at very low level. You see 1.7 picogram TQ per gram. But for the pentosine is pentachloronitrobenzene. We have found very high values of up to 2,400 nanogram TQ per kilogram. And when we included these dioxins in the pesticides, in the pentosine, into the Australian dioxin inventory, already just this pentosine were number 3 dioxin emission from all emission sources. And this is the sediment core from Mexico. This is just published in this is just in Press in Environmental Pollution from Penedo Lopez. It is soil sediment core. The dating starts here, 1900 up to 2003. And what you see here with this sediment core is that we have an increasing trend of dioxins from the 1970s to 1990, 2000. But what you have to consider is that here you have kilogram per gram dry rate. So the Swiss sediment core we had nanogram TEQ. So the Swiss core is much higher. So you are here at a much lower level for Mexico. But what is interesting is that it's increasing from the 1970s to 2000. And the interesting point is that when you look to the dioxin pattern, it don't have a pattern of incineration. It has also very high OCDB, and it's very close to the pentosine pattern. And I know that Mexico has a pentosine production. So it might be interesting to look more in detail. And there are old lists from US EPA and from the German EPA from the 70s and 80s. And at that time, they made a list of chemicals which they suspect to contain dioxin or which they know to contain dioxin. So this is a huge list. But today nobody analyzes the pesticides and these chemicals for dioxins and other unintentional microbes. And I think this is a very interesting research task. So our PhD was very nicely received. We had a big challenge with the ES&T reviewers, but finally we got it accepted. And because of this PhD thesis, now pentosine is stopped in Australia, and pentosine is also stopped in the US. Okay, so now we come to PCB, Stockholm Convention, and research needs. We had this morning already some input on PCB. So for PCB, the main task in the Stockholm Convention is to manage the waste and stockpiles till 2028. And I very much wonder the brimming figure you showed, where you showed this very nice decrease then to 2020. I can tell you that's much too optimistic, because the huge problem we have at the moment is we have now inventory of all PCBs and we have about 6 million tons of PCB waste. We have 6 million tons of PCB waste, but we have only produced 2 million tons of PCB. But of course, when you have then the PCB in the transformer, it's much more waste. And when you then pollute oil with some PCB, 1000 ppm or 10,000 ppm, we get a pollution. So today we have 6 million tons of PCB, and now the task is to destroy this PCB without the release of dioxins and other unintentional effects. And this is really a challenge. Especially it's a challenge for developing and transition countries. So these countries have no or limited PCB destruction capacity. When you look to Brazil, what do you want to do with your PCB? You have limited monitoring capacity. And when you want to export it from South America, for example, in Germany, the price is about $5,000 per ton. For 1 ton PCB. So you could calculate if all the 6 million tons would be processed with $5,000, it would be $30 billion just to manage the PCB waste. When you look to the total budget of the Stockholm Convention, we have a total budget of $1 billion for 5 years. So you see, this is orders of magnitude higher than the whole budget of the Stockholm Convention. And of course we have other costs. So I have looked a little bit in South America and PCB destruction, and I have found that there is a company who sold 2 or 3 mobile small-scale incinerators to Chile and to Brazil. I don't know if you are aware of that. And I also was a reviewer for research on PCB destruction at supercritical water oxidation in Chile. And I just want to show one figure from our research with supercritical water oxidation, which we did in Japan. Supercritical water oxidation is just a hot pressure cooker which you then heat the waste or the PCB with water to temperatures of 200, 300, 400, 500 degrees. So we did that. You see here the destruction efficiency for the PCB for 15 minutes. It was an oxidative destruction. The onset is about 300 degrees. At about 370 degrees, we have within 15 minutes about 50% destruction. And these are always single experiments. All the dots are 15 minutes experiments. And when you look here to the TEQ, what happened from the PCB, furans are formed. So you start here with a TEQ of the PCBs, which is less than 10 micrograms per gram TEQ. And during destruction of the PCB, you form your dioxins, that are your furans, and at the temperature at about 380 degrees within 15 minutes, where you have destroyed about 50% of the PCB, you have increased the toxicity of the whole mixture by 5,000%. And so you really see that you play with fire. And there was also one similar factory, a supercritical water oxidation pilot plant in Germany, in Karlsruhe. They have also destroyed PCB, and one time the experiment went out of control. Since this time, the room is closed. Not open again.
Company as well?
No, it's not a company. This is the Karlsruhe Research Institute. So this was a research pilot scale. And so they had polluted the whole room. And when you are here at 420 degrees in 15 minutes, you have destroyed 99% of your PCB. You think you are nearly done. And when you look to your TEQ, you have increased the toxicity of the mixture by 1,000%. So this is when you think about PCB destruction, TOX destruction, you are really playing with fire. So it's very important to have a rigorous monitoring for it. And this was just a recommendation, and this is not now for this research community because you are more into fish and the environment, but it's interesting for statistics, because maybe you will have to guide your PCB destruction projects if you will do some. So here you will have to think on a strategy how to do a real good monitoring of your PCB destruction. And the problem with dioxin normally is that you just make 6-hour measurements. Then you will have PCB destruction projects which will then go for years. Yeah? So, but there are possibilities to do continuous monitoring. And the question are other unintentional reports and how to monitor it. And I think, especially when you then also include brominated compounds and fluorinated compounds, it's a very big challenge to assess the influence. Yeah? And I think here then we can also move, like the presentation we had in the morning, move to toxicity assessment rather than to assessment of single compounds. Yeah? But this is really a topic to come for research. Yeah? And I think this kind of projects might be an interesting task. So the second part I want to dedicate on PCB pollution in Swiss rivers, because, as I said, we had totally 2 million tons. Maybe today we have released, maybe Frank, you know it better, 20% or 30% into the environment. Yeah, we have the 6 million tons, which might be 30% or so in the stock where we know it, and then we have a large amount of PCB in landfills. Yeah, which are currently not addressed. And when you look into European rivers, you see that a large part of the fishes are above the EU limit for dioxin toxicity from the PCB. One thing what I want to tell, the 2 million tons of PCB, the TEQ of it, I have calculated once. The TEQ of all PCB together is 10,000 to 16 kilogram. Yeah? This you can compare with the 50 kilogram of dioxin TEQ today. Yeah? And when you then have this number, the 10,000 to 16,000 kilogram TEQ, you also understand that when you look into your fishes, that sometimes 90% of your TEQ come from the PCBs. Yeah? Because when we say we release about 30% of PCB into the environment and say, okay, it was about 15,000 kilogram, yeah, we have released about 5,000 kilogram of TEQ just via the PCBs. Okay. So the Swiss found in 2007 that one river was above the PCB, far above the PCB levels of the EU, and then they investigated all fishes in Swiss rivers. So a very comprehensive study, and the aim of the study was to detect possible PCB point sources, develop a methodology to trace PCB point sources, assess the risk for human health, and assess the ecological risk. So there is a report on this project, but unfortunately that's in German. I show you some results of that. Finally, Switzerland found that the fishes in 4 rivers are above the EU level. Like Saane, Hirsch, Aare, and Arche Rhine. First we will look to the Saane. Saane, here fishes in the Saane at different locations. Here, this is downstream of the river. Here we have the TEQ in the fishes, and this is the EU level. Yeah, this borderline for acceptable use for fish consumption. And at this position at La Pina, most of the fishes were above the EU level, 20 kilometers downstream. Yeah, and also about 4 kilometers upstream. Several of the fishes were above the EU level. And this is the source for the contamination of the river. That's an old landfill, used from 1952 to 1975, in total about 2 hectares. PCB levels up to 1 gram per kilogram, and it's estimated that about 20 tons of PCB are in this landfill and are slowly leaching into the river. These are mainly capacitors from a company who produced capacitors. This is Switzerland, pictures of today, yeah, from Marcus Zenek, yeah, from Swiss Empire. And the risk with PCB is when the old deposited PCBs in transformers and condensers, they need years and decades till the whole thing is rusty and that the PCB finally can escape. Yeah? So I'm not so confident about this decreasing level of living. Yeah? Maybe we can do contact to this land. Switzerland is now thinking how to do a complete remediation of this land. Now we come to the second river, that's the Fierce River. Also here, you see the levels of fishes are for several kilometers above the sea level. The glaciers here shorter, 40 kilometers downstream, and the Swiss has now nicely developed a methodology to track point sources. These are passive samples for water. Yeah? And so every 5 kilometers they put some passive samples, yeah? And then they see, oops, here after this position, here need to be the point source between kilometer here and here. Yeah? And they found, okay, it's most probably this factory. This is an old iron factory, one of the earliest producers for cast iron in Switzerland and the last blast furnace, and they use PCB transformers. Yeah, and somehow it seems that they have deposited the PCB transformers or leaked the PCB or in the landfill. So Switzerland is at the moment doing further investigations. And I think this approach of Switzerland is a great approach for our countries. Yeah, just to scan the rivers with passive samples and understand there are point sources for the research, if you have fish problem in rivers. Okay, the last topic of my talk are new crop candidates and support from research community. This is the process how chemicals finally come into the Stockholm Convention. In the beginning, one country has to suggest it, and when you suggest it, then you have to give data for the system, the bioaccumulation and potential long-range transport, and you feed it into the system, and then the reviewing committee does evaluation. This evaluation normally takes 3 or 4 years. You develop a risk profile, and finally you develop a risk management evaluation, and you need information for that, hazard assessment, environmental data, monitoring data, risk evaluation. And these data are actually coming from the science community. At the moment, consultants are gathering this information then from research papers, yeah? But at the moment, not many researchers are involved in this process. And not many researchers are aware what kind of information are missing that a chemical might go up another level. But we have now this hexabromocyclododecane, which was just accepted in last month in the RC6 to continue to the management evaluation. This means just before proposing to the conference of parties. We have 2 science opinions. One is the so-called Northern report, that's a compilation from environmental ministers from the Nordic countries, Norway, which have also suggested hexabromocyclododecane. And they say, yes, hexabromocyclododecane should be listed as crops because it accomplished all criteria. And we have a good science report from Arnold et al., where also Frank is involved. It's called an evaluation of hexabromocyclododecane for persistent and pollutant properties and potential for adverse effect on the environment. And in this report, one conclusion is that the long-range transport and associated hazard is not demonstrated. Yeah, and I think for you, if you are interested in the Stockholm Convention, it's quite interesting to read both of those reports to see how the argumentation works, what needs to be assessed, yeah, and what is the topic now for a very important and contemporary used product. Yeah, and this is at the moment the question: is long-range transport and the associated hazards shown? Yeah, so I'm very happy about that. Here, really, the science community contributes actively. Then the second chemical which is in the reviewing committee are short-chain fluorinated paraffins. Fluorinated paraffins are extremely interesting compounds. Why? They have by far the highest volume of semi-volatile organic fluorinated compounds. We have a production volume today of 350,000 tons a year. This means that within 4 years you produce the amount of fluorinated paraffins which you have produced in history for PCB. Yeah? And at the moment, the production capacity of China and India is just satisfied by 50%. Yeah, they could produce much more, but they don't know in what products. Yeah? So, short-chain fluorinated paraffins are currently assessed for risk profile, and this is already the second round. Already last year it was assessed, but it was not accepted to go step further. And again, some countries were against to move to risk management evaluation, and the main reason they say that they are missing data for long range. So one data which is missing now would be information on long range transport for short chain fluorinated particles, to decide or to go one step more. Without this information from the science community, the report is stuck in the review. I think other very important questions to the research community, considering that we have that high amount of volume, are what are finally the degradation products of these chemicals? Yeah? Because when you, for example, look to the long chain fluorinated particles and the middle chain fluorinated particles, which are not considered NOx, because they are not considered to be mobile, yeah? They are too long. But if they will be oxidized a little bit in the environment, this means hydroxidated or oxidated, they will become mobile. And also when they will be free, they will be controlled. So, very interesting and very important question. And what is this toxicity of the degradation products? Then we come to the last chemical. In the currently in the public reviewing committee, this is endosulfan. Endosulfan has just been accepted from the public reviewing committee to be suggested to the next conference of parties. It's in April 2011 of May. And here Argentina raised the question on the availability and assessment of alternatives for endosulfan, because they have assessed it in their country and they have found some of the alternatives are much more expensive, and they are not sure if all the alternatives will be safe effective. So this is an interesting task for the research community to look to the alternatives. And the last 4 slides I want to dedicate to the process of alternative. For the example of UPOP, that's Doricone. Doricone is not produced and used the last 20 years. You have many of the alternatives, but when you look to the alternatives, I want to highlight 2 parts. I want to highlight imidacloprid, you will see later on why, and the sulfuramide. Sulfuramide is a possible substitute for doricone, and it's PFOS precursor. So that's sulfuramide. This is just amide, and when you hydrolyze it, you just have PFOS. And this is currently the highest used chemical against cockroaches and white ants and fire ants. And my friend from China said that the company producing this sulfuramide, they made a big business with the Olympics and with the Expo 2010, because they produce very much of this chemical for these two events, to keep the cockroaches out of these events. And my friend also compiled the alternatives which are used for sulfuramide in China. Sulfuramide is used in Brazil against woodcutting ants. Yeah? So you are one of Brazil is one of the countries who did quite a strong lobbying that PFOS is very smoothly. They said we need at the moment the sulfuramide because we don't have an alternative for fighting against our woodcutting ants. Yeah? So they have made a calculation. If you would stop the sulfuramide, how much of your harvest, I don't know from which plant, would be lost because of the leaf cutting ants. Yeah? So you are a heavy user of it. And therefore also for you, for Brazil, the question of alternatives is so interesting, like for Brazil. And again, when you look what China is using as alternative, they use as main alternatives imidacloprid. Has anybody in the room heard anything about imidacloprid? Imidacloprid is a neonicotinamide. Has anybody in the room heard anything about neonicotinamide? Yeah? Neonicotinamides are currently the most used pesticide in the world. Yeah? Imidacloprid is one of the most used. What we see is not only a decline in bees in Europe. Just this month, this book has been published, the Systemic Insecticide Disaster. We also see in Europe alarming decline of birds in Europe, along with the increase of insects, contaminated sites. I think that there is a large chance, a large chance in substituting both by better and best alternatives. And I see that environmental research can play here an important role in evaluating the application chemicals which are better, or even then we choose the best as a substitute for forces. And then we don't make the same mistakes we have been
I heard here proposals for about 2,700 PhD theses and so on, and I think it would be interesting to indicate which are the most urgent questions to be solved. The second place I would like to ask you if there are any possibilities, if you think they are very urgent and the scientific community did not start work already, to lobby from the side of the Stockholm Convention Bureau, to lobby with funding agencies like the European Union and similar research funding organizations in other parts of the world to make this a priority, because simply say to the scientific community go on working, that they will not do, because that depends on the funding which is possible for this type of work. And I see in the European Union there's very little money in the next framework program for this type of research. So and also it could be a possibility, I don't know if it's possible, a lot of countries get big loans from the World Bank and GAF to implement the Stockholm Convention. If they would, only 1% would be earmarked for research, that then a lot of researchers can do a lot of work, and it's not done.
No, yes, here you are absolutely right. Yeah, also I tried recently with the new POPs to say we should use a postdoc in Stockholm, and they say no, we don't, we have no funding possibilities at the moment for this kind of research. Yeah, and of course several of these areas, for example for the PPD and the risk assessment, yeah, or the brominated flame retardant and the risk assessment, there are already large research ongoing. One is the ENFIRE project in the EU, yeah, where they make a complete life cycle assessment of flame retardants, yeah. And another very interesting study is funded from the US EPA, and this is about printed circuit boards, yeah, which have to be flame retardant somehow. And at the moment you have here tetrabromobisphenol A, which is the largest flame retardant used. So therefore there is a huge stake for the industry. And there is this research, a project to make the life cycle assessment of all alternatives. Yeah, because one alternatives are the phosphor flame retardants, yeah, which have also some toxicities. Another are the silicates, yeah. But also when you then follow the whole life cycle, yeah, you finally see when you have silicates then in the printed circuit boards, and you will throw it finally in the smelters, yeah, you will have a problem of the PM, yeah, of silicate. Yeah, so for some of the research, there are large projects already. Yeah, I would divide of very complicated research, which have to be like in this EU or America, which only have this funding. Yeah, this might be coordinated by the International Panel on Chemical Pollution. You will talk a little bit. Yeah, that not these kind of very expensive research are done in parallel in different countries, yeah. But there is then also some country activities, like for example to look for the PFC contaminated sites. Every country have to do, yeah. Also Brazil, so they have their own country. But what they can use is, of course, the approaches and the experiences from other countries, yeah. And therefore I have shown these two presentations which we just did for this dioxin conference, where I said, okay, these are really standard approaches, and I think when you come then with these case studies to your government and say, yeah, and now you have signed the Stockholm Convention, that there should be research money. Yeah.
I think that if you look at the OECD guidelines, for example, for admission of new chemicals, they are quite strong. They have a lot of absorption. If it's still working like that, some years ago worked like that, so they have absorption research, a lot of things you have to do. Tedious work. These chemicals, these neonicotinoids, they have been also admitted. They have passed through this procedure. Yeah, but then I would say then instead of doing a lot of research on finding new substitutes, it's also important to have to extend the protocol for these OECD guidelines, that things like this are included.
Yes. Yes, and especially the problem there is that you have many nicotinamides, and then you look today in honey or the bee wax. Yeah, you have afterwards then 20, and afterwards when you do this risk assessment in the OECD, normally you do it for single compounds. Yeah, and so one step further would be yes to include all together, and then only to allow a certain amount of all nicotinamides.
In fact, what I'm proposing, I don't know how to do, but that should be researched by itself already, I think. How to extend the OECD guidelines for this type of products, which are really put inside in the environment, not by accident, but are just put there.
But we see that also now with REACH, which is now I think the most advanced chemical legislation in the world, and made in 2006. Still you have a single chemical assessment, and it's funny. So the triclosan, which you are used, or if the triclosan which you are used as a biocide, is then evaluated differently compared if you use the triclosan as a pesticide. Yeah. So even the same chemical, if it's different uses you make for the peak and PNEC, this is the numbers which you calculate, which are finally in the environment. Yeah. You even not for the same chemical do it in one assessment. Yeah. So this is a big mistake. Yeah, which we I think see here.
And then a completely different thing. I think I talked about it yesterday also a little bit, and I was now discussing with my neighbor during the talk also a little bit. I think there should be made some real effort to have a financing mechanism for research on this type of things you're proposing. Well, I think the major reason, much of this research is not scientifically so very interesting. It looks more like, many of them look like contract research. And contract research has to be paid by someone. And I don't know, we were talking about 1 billion for 4 years at the Stockholm Convention Bureau. Or maybe give to the countries, because there's a lot more money is used for implementation of the Stockholm Convention. For example, in China, the most of the money they borrow from the World Bank, and then they get part of it borrow from GEF, get part of it from GEF. If it would be just made a rule that some part of this money should be dedicated to research, a very small percentage is already okay.
Yeah. So we have a paragraph in the Stockholm Convention about research, but as I said in the first day, at the moment also for industrial companies, I don't see in the national implementation plan a strategy also here to cooperate with developing countries. I think this would be very good, and then it could be also bilateral funding for this work. And at the moment there is not, because there are so many tasks with the PCB management, the dioxin type BEP. These are, if you do then a best available technology project, these are then quickly millions. Also when you do a PCB, and at the moment people see that the money is too less, so people at the moment don't think about research. But I completely agree that also. First, because we have to do it, and second, also for capacity building in these countries. Because after you do this capacity building afterwards, then really the countries can pick up.
At this moment, there is only possibility for university, and that's the audience here, most of the audience, not everybody, but that's the only thing you can do is small, dedicated research efforts at the laboratory level mostly, or maybe a little bit on the field level, and aimed at writing articles for peer-reviewed journals. Yeah? And that the university has a budget for that. Most universities have some budget and have to get additional money and so on. But this is contract research. Most of the things we do. It's not innovating the research.
Roland, I would like to come back to the first part of your presentation. You mentioned the closing, the shutdown of the Böhringer work. Our lab was formed in early 1884. And at that time we did not have very much experience. The German authorities of the environmental ministry, they asked us for the analysis of the so-called residue from this vessel, and we found a value of 0.3 ppm for TCDD. And at that time, we didn't know it at that time, the value for closing a company was 0.1. And the ministry asked our laboratory, well, do you know what you measured there? And we said, well, we know that this is 0.2 ppm. And yeah, this will result in a closing down of the company. And we repeated the analysis a few times because the Böhringer worker, they protested against this analysis, and we found always the same way. So the plant was shut down, but finally the analysis had been performed and confirmed by other laboratories, so it was finally correct. But this was really a time where we had some sleeping problems.
Yeah. No, and so what Olaf said, in 1984, research and also authorities just focused on the 2378, and 2378 was 0.3 ppm.
Yeah.
So afterwards, when you did the full analysis, at that time the TEQ concept was not developed. So these samples, the TEQ coming from the Tetra, was just 1%. Yeah? So actually, the TEQ was about 100 ppm. I mean, the full
I remember
TEQ.
the OCDD content was, I think,
3%. 3%. Yes, you had it percentage.